Let's talk about position vectors and force vectors. They're different things, but position can be represented as a vector and force can be represented as a vector, and they have a deeper relationship that will be useful to us in our course. After today, you should be able to represent a vector in Cartesian coordinates from some given geometry, and you should be able to represent a force that is directed along a particular line. If you think about cables supporting a platform, for example, the force in the cable is directed along the direction of the cable, and so the geometry of the cable governs the direction of the force that is applied to the structure. Now, of course, since this is a virtual lecture, we won't go through all of these items we would typically go through in a typical class setting. But you should open up the slides and go through the example problems, group problem solving problems, etc., in order to enhance your learning. So what are applications of this? Well, here's a ship that's moored to a pier, and the rope is applying force to the ship to hold the ship in position despite waves or movement aboard the ship or whatever the case may be. The rope supports any loads needed to hold the ship stationary. Now, the force in the rope is directed along the length of the rope, along the direction of the rope. And unfortunately, the vector here for the position, R, is a little bit off from the rope. It should be right on top of the rope. I think the author of the slides did this to offset the vectors a little bit, just so you could see them. But just imagine all three of these vectors lying directly on top of one another. Now, why would we care about forces directed along a line? Well, we might need to know how we could vary the direction of that rope in order to control the amount of force within the rope. Because think about it. If you have a rope at an extremely large angle like this, what are you really trying to do? Well, you're trying to prevent the ship from moving around in a horizontal plane, as represented by the surface of the water that the boat sits in. Okay, so the forces you really care about are forces in that plane, but when you angle the rope, the force necessarily must travel along the rope or must exist in the direction of the rope, and therefore there's going to be extra force that's in the vertical direction that really is just fighting the buoyancy of the boat. And so one thing you can learn is that the steeper the angle of that rope, the more force is going to be in the rope and the bigger rope you need. To still get the same horizontal components of force to hold the ship into place. So that's why we care. And then this concept of force being directed along a line will be very useful in your understanding of forces later. Here's an interesting situation where an awning is held up by three chains. Well, why would we care about direction? The steeper the angle of these chains, the less force will be required in the chain, or the more shallow the angle of the chain, the more horizontal the chains are, the more force will be required. Why? Well, the weight of the awning is the weight of the awning no matter what we do. You have to apply a certain amount of force directly upward in order to support the awning. Now, if we don't apply the force directly upward, if we move the chain so that it has some angle toward the building, then the vertical component of the force in that chain is still required to be the weight of the awning. And as you decrease the angle of that chain more and more, so it becomes more and more horizontal, you're going to have more and more force in the chain. Now, the chain probably won't mind. Most chain are fairly strong, but notice these chains are anchored to the building and could eventually pull out of the building. And so we're very interested in forces and their directions because they are very useful in applications. So let's talk about position vectors. What is a position vector? Well, it's defined as a fixed vector that locates a point in space relative to another point. That's really what a position vector is. And so you see point A and point B in three-dimensional space here. The position vector locates vector B relative to vector A. So how would we represent it? Well, if we consider points A and B, you'll notice that A and B both have X, Y, and Z positions. So, for example, the X position of A is XA, the Y position of A is YA, etc. Same thing for B. In order to actually write down the position vector, what you would have to do is to take the difference between those two, because what we're really interested in is how far do I have to move along the x-axis to get from A to B? Well, along the x-axis, I need to move xb minus xa. Along the y-axis, yb minus ya, and along the z-axis, zb minus za. So we're simply taking the difference in the coordinates of these 2 points in order to represent the lengths of each side of vector r. And so you see that the vector from A to B, so RAB is read as the vector r from A to B, is equal to xb minus xa in the I direction, the unit vector pointing parallel to the x-axis, plus yb minus ya in the j direction, which is the unit vector pointing in the same direction as the y-axis, or parallel to the y-axis, and so on and so forth for the k direction along along a line parallel to the z-axis. So now be careful. Notice that the vector begins at A, that's the tail, and goes to the tip B. So B is the ending point and A is the starting point. In order to represent the position from A to B, you have to always be careful to subtract the tail from the tip coordinates. If you do it the other way around, your vector will be in reverse direction. So we've already pointed out some chain and rope that have force in them, and obviously that force is directed along the length of the chain and rope, because you can't push a chain, you can't push a rope, right? Well, if you got it, you can, but that's another story. Anyway, so if force is directed along a particular line where we know the geometry of that line, then we can represent the force vector by using a unit vector from the position information. So what we would need to do, first of all, is determine the position vector. Which way is the rope pointed? What are those coordinates? How do we write that as a vector? And we can do that by finding 2 points along the line. Then find the unit vector, which represents that direction. So UAB is calculated from the position vector RAB. You'll notice we simply take the vector RAB itself and divide it by the magnitude of that vector. And then we simply multiply the resultant unit vector by the force in the rope or the chain or whatever the case may be. And that then yields a force vector directed along the rope or the chain.